definition of the ampere. Well, let's now talk about the magnetic field at the center of a circular loop. If I take a wire and bend it in the form of a loop, what is the magnetic field at the center of it? In order to find the magnetic field at the center of a circular loop, we take a small current element IDL that has a radius R. Now this is a circular loop. We take a small current element IDL on that loop. Now this is the current element IDL. And you know, we have talked about earlier that IDL is a vector. And we find the magnetic field due to that current element. Is that right? At its center. Now the magnetic field dB at the center of that loop due to this current element IDL. Can you write that equation from what we discussed in the earlier class? Will be dB equal to mu 0 over 4 pi IDL sine theta over r squared. It's actually Biot-Savart law. Alright, so the magnetic field at the center due to this small current element IDL is mu 0 over 4 pi IDL sine theta over r squared. There you are. Now, theta is the angle between the current element IDL and R. In this case, that theta is 90 degrees. Is that right? So, since the angle is 90 degrees, sine theta is 1. And therefore, we have dB equal to mu 0 over 4 pi IDL over r squared. And to find the total field at this point, we need to find the dBs due to all such current elements and add them all together. In other words, we do an integration. So we can say B equal to integral of dB, and integrating dB, what is dB equal to? Mu 0 over 4 pi IDL over r squared. Since sine theta equal to 1, we don't need to worry about it. And in here, mu 0 over 4 pi is a constant. R, the radius of the while loop, is a constant. And the only variable there is dl, the length of that small loop. So, we can take mu 0 I over 4 pi squared outside and integrate dl. What do you get if you integrate dl? Well, integration of dl will give you the total length of the loop, which will be 2 pi r, the circumference of that loop. Therefore, that will be mu 0 I over 4 pi squared times 2 pi r, or that will be mu 0 I over 2r. That's an important result. The magnetic field at the center of a current carrying loop of radius r is mu 0 I divided by 2r. Another example. 1/4 of a circular while loop carries a current I. Find the magnetic field at O, the center of the circular coil. Well, this time we have just 1/4 of a while loop. And that is the IDL that we're going to choose there. And the vector R is the radius of that loop. So the current element IDL is at a distance R from the center point O, and where R is the radius of that coil. The field dB due to one such current element is, how much is the field at the point O due to the current element IDL? Will be dB equal to mu 0 over 4 pi IDL over r squared. What happened to sine theta? Sine theta is 1 because the theta is the angle between the vector IDL and the vector R, which is 90 degrees. Now the magnetic field at O, due to the entire length, will then be obtained by integrating dB for the entire length. In other words, integrating that dl. So that will be mu 0 over 4 pi I over R squared integral dl. And integrating dl here will be 1/4 of 2 pi r. Is that right? Because the whole of that will be a circle. This is only a quarter of the circle. And therefore we have mu 0 I over 4 pi r squared, this quantity, and integrating this will give you 1/4 of 2 pi r divided by 4. And that will be mu 0 I over 8r. If you cannot see this on the screen, please refer to the printed PowerPoint slides. We will now obtain an expression for the magnetic field at a point on the axis of a circular loop of wire like this. Now, this is the circular coil and this is the axis. Any point on the axis is our subject. Alright, so we will start by considering a point. Consider a circular loop of wire of a radius r carrying a current I, and that is the axis of that circular loop. Let's take a point P on that axis, which is at a distance x from the center of that loop. Now, we will take a current element IDL. Our aim is to use the Biot-Savart law. Now, do you remember that law? We take a current element, say IDL, over here, and obtain the magnetic field dB at P. Then we will integrate that dB over the entire length of the circular loop. That is the idea. Now, you know from our earlier discussions, Biot-Savart law, the magnetic field at P due to the current element IDL will be mu 0 over 4 pi times IDL divided by R squared, where R is that distance. Now remember, this dB will be perpendicular to both R and IDL. That means sine theta equal to 1. Now, this R can be replaced. The square of this R is the radius big R squared plus x squared. So we're going to replace this R squared as big R squared plus x squared. That gives us the expression dB equal to mu 0 over 4 pi IDL over R squared plus x squared, where R is the radius of the circular loop. Now, very often in this lesson, sometimes in place of magnetic field, I mistakenly say electric field. If you hear that, substitute the electric field with magnetic field, because we are now studying the magnetic field due to an electric current. Now, this dB is actually in a direction such that the angle theta, which is the angle theta. Now, if you know this angle, you know that this angle is the same as that angle. Is that right? I think so. That means the dB makes an angle theta with the vertical. Now that means dB has an x component which I call dBx and a y component dBy. Now, When you take a current element on the top, that is what we have done, it has this x component and this y component. How about you consider a current element diametrically opposite? If you take a current element here, dB will be somewhere in this direction. It has an x component and a y component. Now notice that for this element, if the y component is positive, for a current element here, the y component will be negative. For each current element, there is a corresponding element diametrically opposite, so that the y component of dB will all cancel. That means only the x component will survive. Alright, so a similar current element diametrically opposite to this one will produce a field dB at P such that it has an x component dBx and a y component dBy, and all the x components are in the same direction, but the y components will all cancel. They will not survive. And so we need only worry about the x component, which is dB sine theta. If this angle is theta, the x component will be dB sine theta. Well, dB we know is mu 0 over 4 pi times I dl over r squared plus x squared, and sine theta from this diagram is r divided by the small r, and this distance is square root of r squared plus x squared. So this expression replaces sine theta. Sine theta is r over square root of r squared plus x squared. Now combine all these, that will give you mu 0 I r divided by 4 pi times r squared plus x squared to the power of 3 over 2 times dl. All these quantities are constant, so we need only integrate for dl. So the net field B is obtained by integrating this dB along the length of the circular loop. Alright, let's do that. So B will be equal to this quantity that remains a constant times integral dl. And what does integral dl give you? The total length around the loop, which is 2 pi times capital R. And simplify that, it gives you this expression, mu 0 I r squared over 2 times r squared plus x squared to the power of 3 over 2. Now, this is the exact expression for the field at a point at a distance x. Let's consider a case where this x is very large compared to this radius r. In that case, this r can be ignored, and therefore the quantity r squared plus x squared to the power of 3 over 2 will simply become x cubed. Is that right? And so we have an approximate expression for the magnetic field at a large distance from a circular loop of wire as mu 0 I r squared over 2x cubed. If you remember, this is similar to the situation we discussed in static electricity. Okay, let's use this to solve